Hello and welcome to the final episode of the full 2024 New York City Category 30 seminar. And today we're having Matthew Cushman,
Recollement or recollements, depending, whichever is less embarrassing.
Go, take it away.
Thanks. Recollement or recollements, I'm honestly not sure which is like less goofy. I'll just switch back and forth to get the maximum amount of goofiness. So recollement and Artengluing are two names for the same sort of core idea. They really amount to the same thing. Maybe I'll just briefly give a little, to the extent that I know the history. Both of these concepts go back to SGA4 in the 60s, Grothendieck and Verdier, and they have sort of they sort of follow two different tracks through the literature, as far as I can tell, with Artengluing being the track that runs through topos theory, and recollement being the track that runs through abelian categories and triangulated categories, so more the algebraic geometry side. But they both are essentially the same thing. So, in order to motivate the idea of a recollement, let's consider a sort of motivating example, like a prototypical example. So let X be a topological space. All right, let X be a topological space. Let me just draw something so you have something to look at, which is always nice. And let K be a closed subset, and U be an open subset. So we have a topological space X. I'm going to draw the closed side. It's a little bit hard to sort of indicate on the board, so I decided that this is what I'm going to do. So this is going to be, maybe I should leave myself some room. So this is going to be the closed subset of X, and this is going to be the open subset of X.
U is the complement of K, not just an arbitrary other opens.
Yeah, it's the complement, and I'm drawing it because this sort of makes you feel like the boundary is in K, which is what you're supposed to feel. Sure. So that's the idea. So here's the picture, and of course, if you have let's just draw like some open set in X, let me just call it A, then of course you can restrict to either of the two sides. So let me maybe, I'm going to need an eraser to grab this. So you can restrict to K, and you can restrict to U. And of course, these are going to be the two restrictions. This is U. All right. So if you consider the post set of opens of the topological space X, then these restrictions give you functors from the post set of opens on X to the post set of opens on K and the post set of opens on U. And both of these functors are left exact, meaning that they respect intersections. All right, so the sort of parallel picture is like opens of X, and we have a restriction, which I'm going to call I upper star to opens of K, and we have a restriction that I'm going to call J upper star to opens of U. And these letters are sort of the typical choice in the literature, so I didn't just make those up. All right. Okay. So all right. So we have these two restriction functors. Okay. So the question that I want to address is basically if we know the post set of opens on K, and we know the post set of opens on U, we have these two post sets, then what sort of extra information do we need to be able to reconstruct, like maybe I'll say topology. If we know the topologies on these, what information do we need to be able to reconstruct the topology on opens of X? So that's the question I want to address, right? So in particular, you can ask the question, if I had an element of open of K and I had an element of open of U, then under what conditions will these be the two restrictions of an open in X, right? So certainly not any pair is going to come from an open in X. So for example, suppose that we just started with a, maybe I'll choose, so this is an open set in K because we're giving K the subspace topology, right? So this is an open set in K, and it does include the boundary there. And then maybe just like, I don't know, choose the empty set for the moment, okay? So imagine the empty set. So I have a pair, this open set and this empty set. When I look at their sort of preimage upstairs, it looks like that, which includes this piece of boundary and is clearly not open in X, right? So that would be an example of a pair that does not satisfy some condition. All right. So how can we figure out what that extra piece of information we need is? Okay. So what additional information do we need? Maybe I'll just write. So not all opens, maybe I'll call the A one A in op K and B in ops of U come from an element of opens of. All right, so in order to come up with the condition that we need, let's consider the following, all right? So let's start with an open set in U here. So let's start with an open set in U, call it B. All right, so let me make sure I'm doing this in the right order. So let B be in opens of U. All right. So clearly, the condition that we're looking for is going to have something to do with how these two open sets like interact with each other in X, and in particular, something to do with how they line up on the boundary, right? So if we have an open in B, there are two ways of constructing sort of an inverse, right? There's one way is that we can take an open set in B, so like one of these things, and we can just include it back into the original space. Clearly we will get an open set in the original space here, but that's kind of boring. So if I do that, it'll restrict back to the original set, but it doesn't interact at all with the closed side. So maybe you could think of this as the boring adjoint. Maybe I'll say, so we have, did I mark these? So this is I restrict, and this is J restrict. So there is a J lower shriek that takes B to just B in X, right? B subset of X. Sort of the minimal solution to a set in X that restricts to B. And then there's also the maximal solution. There's a more interesting functor, which I'll call J lower star. And this is going to be defined as, I will write it like this. Sorry. U implies B. So if you've seen this notation before, then this is the sort of, the implication in the, if you think of this as a locale, then you have it's a closed category.
Right, the point is your opens are Cartesian closed. So.
Yeah, so these post sets, these are actually locales, which you can think of as, but anyway, but this is sort of like the fancy way of writing it, but what it amounts to in this case is, it's like, it's going to be the interior of the complement of U union B. Complement of U is K, so it's just that. Right? The interior of K union B. So what this amounts to is you take your set. Sorry, this would. The adjoints.
Let's forget the direction, the left and right.
Yeah, so the left one is going to be the shriek one, the boring one, and then the right one is going to be the one we're going to end up caring about. And these are left adjoint, so left adjoint to this, left adjoint to that. So J lower star is left adjoint to J upper star, which is, I guess
Thank you, J upper star.
this is J upper star here. All right. So J lower star is going to be right adjoint. J lower star is right adjoint to the restriction. Okay, so what this amounts to is the following. So if I start with an open set B, maybe I will sort of make another picture over here to get the idea. So the idea is the following. I think I drew out some. So here are some examples of what this ends up looking like. All right, so if I start with B, and this is U here. If I start with an open set B in U that is like away from the boundary, then what I'm going to end up getting upstairs, so this is J lower star, is going to be B, so that when I restrict, I get back what I started with, union, and then here I'm going to actually draw it like that. So the idea is that this is the interior of K, right? So it doesn't include this boundary here, right? So this is maybe call that the interior of K. Interior of K. So that's what it looks like if B is sort of away from the boundary. If B is, draw another one of these blobs. Let me make it less ugly. I'm trying here. So I'm going to draw something even worse. Okay. So if we start with a B that is right up against the boundary like this, let's see, then what is this going to look like? So this is actually going to end up looking like, so one way to describe this, by the way, is this functor, by the way, is to say that it takes B to the largest open set of X that restricts back to B. The largest, so.
That equals to the interior of K union B?
Yes.
No. Interior of K union B.
Oh, in this case it is, yes.
Well, no, he's
No,
about,
not always,
no,
not
he's about
always.
to show you the case where it isn't.
Yeah, so that's exactly what where things get interesting.
Yes.
So if I have a B that's right up against the boundary like this,
You're right, yeah.
then what's going to end up happening is that there's going to be
There's some boundary there.
some boundary, exactly.
Yeah.
So I don't know how to draw it. I think that's pretty
So in other words, it
evocative, right?
includes part of the boundary.
Yeah,
exactly.
Versus when it's outside, that means, okay.
Exactly.
It's without the boundary. Okay,
Yeah,
interesting.
so the cool thing about this fun adjoint is that there's some information that you get that talks about, that somehow encapsulates whether this is close to the edge or not, right? So, all right, so that is the left adjoint. So now,
Yeah, the interior K could be empty.
so now we can apply the closed restriction. So if I restrict to K, if I restrict to the K side from both of these, then I get, if it was away from the boundary, I get the interior of K. If it was up against the boundary, I get the interior plus a little piece of the boundary on, which tells you sort of where it lined up, right? So that's the idea. So now we apply, let me write it, I upper star, J lower star. Okay. So, okay. So, and we get, let me see, just like comma, dot, dot, dot. Okay, so let me maybe go over here. Okay, say goodbye. All right, so now we have a, now we can sort of figure out a criterion. So if A union B is open in X, so let me say, start with A in K, sorry, subset of K, and start with B, subset of U. Let these be. So if A union B is open in X, then surely A union B is a subset of J star of B, because this was the maximal open in X, and that gives you back B, and so surely this is a subset of that. Okay. When I restrict back to the closed side, I get that the restriction by I of both sides, I restrict J push forward of B, I get that this is a subset of that. And then this is just restrict to the closed side, so that's just A. So A is a subset of I lower star J, J lower star of B. All right, so this is a, so if I have an A and a B that come from an open in X, then this must be the case. This must be a subset of that. It turns out that this is not just necessary, but sufficient for a set to come from an open. So let me just briefly explain that. Okay. I'm gonna erase this. Okay, all right, so A turns out subset of I upper star J lower star B is necessary and sufficient. For A union B to be open in X. All right. All right, so we can define A. So I didn't define a right adjoint to the I, the closed restriction, so we can define a right adjoint I lower star going from opens in K to opens in X, right adjoint to the restriction, by just taking, so send, I was calling these B, right? No, A. So I lower star of A is just A union U.
But in this case, you're not going to have a minimal one because the thing is
Exactly.
is closed, not open.
Exactly, exactly. So this is the maximal one, but there really isn't a minimal one, right? So this is the okay. Then A union B is the intersection of sorry, this is a J. All right. So then A union B is the intersection of these two. This is easy to do, so I think I'm just gonna, but I think I'm just gonna skip it. Like basically, I'll just say it in words. Like if you intersect this with U, you get B. If you intersect this with K, then with a little quick calculation, you find that you have to use this condition. But if this condition holds, then you get back B, and therefore you have an open. That restricts to give you A and B upstairs. So I'll just leave it at that. All right. So that's the. This is sort of the motivating. Example for the general story. So let me get to that. I'm going to erase this. All right. So, but the short version is all we need is, in order to reconstruct the topology on X, the opens of X, all we need is opens on K, opens on U, and a left exact functor I upper star, J lower star, going from opens on U to opens on K. These were the three pieces of information that we need. These are the three pieces of information that we need to be able to reconstruct. The topology on X. All right. Let me just point out one thing. So this functor, take an open in U, take the sort of maximal thing upstairs, and then restrict down to I and include some information about the boundary. Clearly this is sort of non-trivial, but the other way around, so note that if I do this the other way around, so if I take a closed set and then I take the maximal thing upstairs by just taking the union with U, and then restrict by taking the intersection with U, I always just get U. So I always get U. And notice that U is the terminal object in opens of U. So this equals the, I'm going to call my terminal object star. So
the important thing here is that you didn't need I and J separately, only this combination. Well, because you only need this one combination.
yeah, so this,
Only an I and J to define separately, I only need this combination.
No, but,
Yeah,
and you don't need
so-
A or U either, you can just start.
you literally just need, you literally just need this. If I have an open on, if I have a
You just
post
need
set of
an
opens on X, post set of opens on U, this thing here, maybe you could think of this as the gluing functor. By the way, recollement is French for gluing. So art and gluing, recollement is just two different words for the same thing. So this is like the gluing functor. And that's all you need, this, and that. All right, so I'm gonna say more obviously in just a sec. Let me erase some stuff. Sorry, I'm trying to hustle a little bit because I got here real late. All right, so now let me actually, so I want to do another fun example, but before I do that, I'm going to give you the actual definition and stuff like that. So let's get to the meat of it. So definition, what exactly is a recollement? So let's see, be a category with finite limits. I'm sort of, so let's see, be a category with finite limits. It can be an infinity category. So it can be an infinity category, whatever kind of a category. I'll just say category.
See, the post set, the limits just mean we have unions.
Intersection.
Or
Yeah, intersections.
Oh, intersections.
Right,
Okay.
right. So this is the most general definition of recollement that I could find. And by the way, this comes from Appendix A, point 8 of higher algebra. That's the only place that this has been, that anybody has written this down, but it's like, it appears to be, like, I would take it to be like the standard definition, all right? So we say C is a recollement, or recollement, depending on what you feel like saying, if is a recollement of, let's call the two subcategories curly K and curly U, closed and open, if there is a diagram of categories and functors like so. So we have C, we have curly K. So if there is a diagram C, curly K, probably want to give myself a little more room. So let's do curly K, C, curly U. We have the push forward I lower star here, and the left adjoint, the restriction I upper star. So using this for left to right adjoint. And then here we have the J upper star, the restriction, and its right adjoint, J lower star. So you have this setup of categories. And I'm drawing it like this for a reason, like that we'll see hopefully later, that in certain situations you actually get the other two adjoints. So, but this is the bare minimum to have a recollement, such that, all right, and then where should I, maybe I'll just do these up here. So condition one, I star, lower star, and J lower star are fully faithful. Fully faithful. And I'm just going to say replete. So I don't think this is like typical terminology for a functor, but I just mean that anything isomorphic to something in the image of one of these two is also in the image of one of these two. So the subcategories that these pick out are replete subcategories, closed under isomorphisms or equivalences. Okay, fully faithful and replete. Two, I upper star and J upper star are left exact. Okay. I upper star and J upper star are left exact. So in particular, you have a fully faithful right adjoint, left exact. So you can effectively think of K and U as both as reflective subcategories of C, and if C is like a topos, then they'll be subtopoids. All right, subtoposes. But basically, you're free to think of these as subcategories of C. All right. Three. J upper star, I lower star equals the terminal object of U. So maybe I'll say term obj of U.
So the uninteresting composition you had a moment ago.
Yeah, exactly. So this is sort of like, this ends up being sort of like an orthogonality condition, or maybe there's actually a nice way of thinking about it that if I do I and then J, I get 0. So this is sort of like it'll end up being like an exact sequence, kind of.
The whole thing has
Sort of like an exact sequence.
the whole thing has a feel of an exact sequence.
It's-
when you have good functors, then C is a product of K and U.
Yeah, exactly. In fact, there's a cool paper that I can give you a reference to that actually makes it precise. That in fact an art and gluing for toposes. I mean, C doesn't have to be a topos, but if we're in topos, like one topos land, then this is basically like a semi-direct product, where it's analogous to a semi-direct product where this is like the normal subgroup and this is the complement, and you can make all that precise, like. And it's very cool.
What paper
So,
is
it's called,
Where's the author?
crap, I have to remember. I have it in my thing. I think it's Art and Gluings and Split Extensions or something. I don't know. I can't remember. I'll get it to you after at the end of the talk, though. So anyway, we have this condition 3, and then condition 4 is that the two localizations, the two reflectors, I, lower star, I, upper star. It's going to be so annoying writing all these uppers and lower stars.
It's probably going to be FAUL, Peter F. Fall, and Graham Manuel.
Exactly.
Yes.
Siqueira. Fall, Manuel, Siqueira, right?
Well, there's a couple different papers. The one I found doesn't have that as a co-author, yeah.
Oh, the one that I was thinking of, I think it's literally called Art, the name of the paper is Art and Gluings and ... Like I have it in my folder as Art and Gluing, so I don't remember the rest of the name, but I'm sure you could dig it up. It's really cool.
There's one with as adjoint split extension.
As adjoint split extensions, exactly, that's the one.
And then, there's another one that is Art and Gluings of frames as semi-direct products, and that's that's more recent.
I think it was that. Well, anyway, I'm sure they're both pretty much very similar or whatever.
The author of that semi-direct product.
Also Fall, FAUL.
And Manuel.
Yeah, so a recollement is basically a semi-direct product of categories. I think it's fair to characterize it that way. So, and then the last condition is that the two reflectors are jointly conservative. Jointly conservative. So, which means that a morphism in C is an isomorphism if and only if it's an isomorphism, if and only if both reflections are isomorphisms. So they both have to be isos, and then it's an iso. That's what jointly conservative means. All right, so that's this is the official definition of a recollement, which is the same thing as an art and gluing if you're in the context of toposes. It's the same thing, all right? All right, so let me write a couple fun facts.
So
I guess I'm gonna go.
Subtoposes, when they're toposes?
K and U,
So if,
that's the right terminology.
if C is a topos, these are required to be, so this is left exact and this is fully faithful. So this is a left exact reflection onto a subcategory, which is a subtopos.
Okay.
So it's like if you're, maybe, you're the expert on this, like maybe if C is a Grothendieck topos, then for sure this is the case, but if it's an elementary.
So sort of what's happening is that the recollement of two categories is going to be, in some sense, like the least category, or, well, it's not the least, it's A, there can be many of them, so it's not uniquely defined or anything, right? Or is it?
Yeah, so it's defined by this data. Like you could sort of think of it like the way the semi-direct product works is like if you have a group, then you might be able to recognize it as a semi-direct product of a normal subgroup and a complementary, non-necessarily normal subgroup. That's like the internal semi-direct product. So that's sort of like, this is more of the internal perspective. But then there's like the external semi-direct product where if I have two groups and I have a certain extra bit of gluing information, then I can sort of create a semi-direct product such that it is the semi-direct
I guess,
product.
okay, so let me state something and then ask a question. So
Go for it.
it's an object, or it's a category such that both of your other categories, your K and U, are reflective subcategories of some sort.
Yep.
And then the question is going to be, is it going to be, like, if you can compute it, is it going to be in some sense the least such thing? Or can you have like a whole bunch of them that are totally different, and this is just one of many?
Certainly in the group case, you can have many,
Yeah, you
two
could-
groups I can make semi-direct products.
Yeah, there's no
They say,
reason-
all I need is an action of one group on the other group, and I get, for each action, I get a different.
I got it,
Yeah.
because it's
So-
gonna be, you're gonna be gluing along these inclusions. So
I mean, yeah,
it's
given
such, yeah.
given a category, there could be lots and lots of pairs of subcategories that give
Okay.
you this, and there's a whole category of recollement even, and there's lots of
Okay.
so there's lots of possibilities for which to basically just, if you have a subcategory and another one that are sort of orthogonal in this way, then
There's a couple,
that gives you
different arrows too.
that gives you a recollement, like a decomposition maybe of C as this recollement of these two categories.
Okay.
Right? So all right, so the reason that these recollements are so cool and useful, or maybe one of the reasons, can I erase this, is the following theorem. All right, so theorem So let C be a recollement of K and U okay. Then you get the following diagram. So let me draw it first and then I'll talk about it. So you get a diagram of functors. So this is the identity functor on C. Going down, you have the unit of the I adjunction, which gives you the reflector. So this is going to be I lower, I upper. Maybe I'll call that unit sub I. Okay, and then this way you get the unit sub J. So this is the reflector. This is the sort of reflection onto the open subcategory. So J star, J lower, J upper. And then over here you get, I'm bringing a lot of these little I's and J's with little stars, like, I don't know, it's like okay. So you get a commutative diagram like so. Let me just try and make it a little more symmetric. So here we have I lower, I upper. All right. So in general, this diagram, okay, so let me say what the maps are. So this is the unit I, and then this is the unit, the I unit, sort of applied to
J.
to this thing,
Yeah.
right? So this is the I unit. Rather than put it in the subscript, because I already have an I there, I'll just write it like this. Right? All right?
Yeah.
So this is the unit applied to this thing, whiskered or whatever. So, okay, and then...
Likewise with the bottom one, just using...
And this is the composed on the other side, right, exactly. So this is the J unit, I applied to, I lower, I upper, applied to, okay? Whiskered on the other side. So this diagram commutes because this is a naturality square. So we have this natural transformation here. Here's the component of this natural transformation at, let's say, an object X or something. And then we have J lower, J upper X over here. And then this is the component at J lower, J upper X. By naturality, this commutes. But if we're in a Recollement situation, this is a pullback. So we get a pullback square here. And this pullback square is called the fracture square of the Recollement.
Who calls it that?
Everybody calls
Really?
it that. All the cool people call it that. Yeah. No, this is you know, not just, this is like standard thing. Like this is where fracture squares come from. So maybe you've heard of fracture theorems like in homotopy theory, can sort of like fracture homotopy theory into like rational homotopy, and homotopy is at various primes and stuff, and then piece together the homotopy. This is the same exact thing in the correct, you know, changing the things you need to change. So this is the fracture square of the Recollement. So you can sort of, so the example we just did, we had that any open set in X was an intersection of sort of two of these pieces, like you can sort of connect it to the other thing. But let me just say how you prove this.
That's why it's called a fracture square.
Yeah. So the idea is that, so essentially we have the original category C here, and this is how you can sort of break it into two pieces. Like, but how you prove this is very straightforward. Like it's, so if you apply the localizer I lower star, I upper star, I need to come up with a better name for this. Let me call this the closed reflector, the closed reflector. So if you apply the closed reflector to both sides, so hit the whole diagram with this thing, not both sides, but the whole diagram, then you get essentially the identity over here and the identity over there. So you have a pullback square. And if you apply the other reflector to the whole diagram, then you get, so I have j lower, j upper, apply that on the left of the whole thing. On the top, I get the identity. And on the bottom, I get the identity map at the terminal object, because the j upper, I lower gives you the terminal object. All right.
In what category? All endofunctors of C? Is that what you're saying?
This is a diagram in, I guess, yes, endofunctors of C. Exactly. So these are all endofunctors of C, and these are all natural transformations.
Oh, yeah.
Yeah, that is the case. So this is the fracture square. Yeah. So if you hit it with both localizers, you get pullback squares, and then it follows from the jointly conservative condition that this is a pullback square. Maybe if you can think of it like, think of the sort of the Cartesian gap map is what I've heard it referred to for this square here. Just if you reflect, you get an iso. So by the joint conservative property, the gap map must itself be an iso, and therefore it's a pullback. So that's the idea. So it's a very, falls right out of the definition, right? So this is the fracture square, and then what am I supposed to talk about? Okay, let me just talk briefly about the sort of external recollement, so how you make a recollement out of the bits of data. I guess this data right here. I'm gonna have to erase this. Okay.
Are you gonna erase it and replace it with a more general version?
I thought you were going to prove that C is a comma construction of K and U.
It's funny that you say that, because that's literally the next thing I'm about to write. You are way ahead of me.
I thought that's what you were going to.
I'm just about to do that. So let me call this external recollement. External, sorry. External recollement. So if you have a category, so given cats K and U, and a left exact functor. I usually use whiteboards in my day-to-day. So chalkboards they have a really different feel to them. And a left exact functor, that's my excuse for my horrible handwriting. And a left exact functor F, going from the open
other
to...
times when by whiteboard, you have the excuse that I grew up learning how to use chalk for blackboard.
Yeah, I like whiteboards. Like, I know it's like sacrilegious, but I'm kind of a whiteboard.
I've heard enough.
Yeah, he's out. He's leaving.
So now we have an adjoint pair of excuses.
Yes, exactly. So given the data as two categories and a left exact gluing functor like so, one can form.
You see what you drew after saying that silly thing in that whiteboard.
Jesus, Matt.
Oh. I'm just like, I got too much on my mind to notice things like
Well,
that.
there is a C around somewhere.
One can form the identity.
Yes, that's what he's gonna produce.
Oh, boy.
So one can form this comma category here. So I'm just using the typical comma category notation. So we have the identity functor from K to itself, and here's the functor from U to K, and then this is going to be the comma category. So it's the category whose well, let me just write it. So elements, so objects are triples of the form. Wow, I really am not very conservative with my use of board space. Are triples K, U, phi, let's say, where K is in K, U is in U, and phi is the arrow. So phi is the arrow from K to F of U. So And phi is the arrow from
Is between you, okay.
K to F of U. Yep. So, yeah, so this is a comma category. And then the fact, the theorem, I guess, is that this will be the recollement of K and U, all right? That's as simple as
I guess
that.
in my analogy, your earlier thing, the F will be that composite of I and J, that extra piece of data you needed.
Exactly, exactly. So the idea is, maybe let me just say a couple more.
Generalizing what you erased to write this.
So objects are triples like that, and let me just write it. So identity functor on the comma category that I just described is a recollement of K and U curly.
By the way, it also answers Gersham's earlier point, because as many of these things as you'll have such functors.
Yeah, that's what I was gonna say, so that's really the missing, you're gluing K and U along a functor.
Yeah,
And
yeah.
I guess something I'll mention here, right, although you might get to it later, is I think there's an interesting case in particular, or a common case when K is discrete.
Yes.
Yeah, that's like.
Scones.
Yeah, yeah.
Sierpinski
That's what
cones.
I know most about, yeah.
Yes, exactly, yes. I came across those when
Yeah.
I was reading about this.
What's the
Yeah,
name of this case?
this, what case?
Special case.
It's called sconing or gluing along the Sierpinski cone.
Okay.
And it's because if you've got a space and then
Here, I'll let you
the
talk
data you're
while I-
gluing
Right.
is just like a fact about that space.
Understood.
But then you're sort of gluing the space to itself in a sense along, along some piece of like binary knowledge if it's a Sierpinski thing, or like, but you can do ternary knowledge or anything else.
Okay, thanks.
Yeah, it looked super interesting. It's like something like if you have some category of objects that don't have underlying sets, then you can sort of create underlying sets in some weird way that, like, I don't know. It sounded really interesting, but I didn't have time to think about it. So
This is what John Sterling's thesis was all about, just want to mention.
yes, that name I came across because he has writings about this art and gluing stuff, and unfortunately I wasn't able to dig from his website his actual notes on art and gluing, or it would have saved me a lot of trouble when I was preparing this. So this is all pretty classical stuff. Like, this is like topos theory that's like pretty well hashed out. Which I guess I'm not like a topos theorist, so I wouldn't know, but apparently it's pretty,
It's in the elephant.
yeah, it's in Johnstone and all that, yeah.
But just thinking about the group thing, semi-direct product, there the extra data is a map of action of one group on the other, so this functor is the analog of that.
Yeah, exactly.
yeah, exactly.
That's exactly right, yeah. Yeah, no, like I said, the analogy goes through like perfectly at the end. Like, you can really make it like literally the same thing. So, all right, so this comma category is the recollement of these two things, where we have, let me just finish writing the other two functors. We have, U, comma, identity on F of U. So, right, so the restrictions are just the sort of obvious projections, right? So the closed restrictions just project out this, open, project out that. The other adjoints, the right adjoints, are given by take an element of the closed category and just
Map it to the terminal.
send it to the arrow that goes to the terminal object, exactly. And at some point I must have required that all my categories have finite limits, so let me just say
Yeah,
like that there is a terminal object, all right?
You mentioned that.
Yeah.
All right, right over there, right?
Yeah, yeah, it's up there somewhere,
You got it.
so add that in wherever it needs to be said. So this is
And the
the,
exclamation is was the subset,
No, it's a unique
Unique
map.
map.
This is just
Is that what that means?
the map to the terminal object.
Okay.
Yeah.
And then
So
what's the bottom?
typical notation for that. And then U here says that if I have an object U in the open topos, then I can just
The FU and-
let the closed object sort of, I think of my arrows in the comma categories going down like this, like let the object on top be f of U, and then of course U gets sent to f of U, and then I just take the identity arrow between f of U, and that's an element of the comma category, object in the comma category, that gives me the right adjoint for the open restriction here. And then all this, you can sort of go through it, gives you a recollement. It all satisfies all this stuff. So I'll leave it at
This is
that.
now the external definition.
This is, yeah, so if you have
It's a way of constructing.
a way of constructing a recollement, yeah, exactly. So let me see, how am I doing on time? What is it, 8, 7, I don't know. So the next thing I wanted to do, right, so I want to show you a cool example. So I definitely need to do this example. So let me just let me state a couple of facts and then give you a cool example. So open-close decomposition, decomp of a topos. Okay, so if we are in the context of an actual topos, let U be a subterminal object okay. Then there are two localizations that we get. So we can define the open localization to be J upper star. So I'm going to think of this I'm going to think of the open subtopos as a subcategory.
So
So I
you're
don't have to
fixing
include
a
that.
recollement of a topos.
No, I'm going to create one. I'm saying you have a topos and you have a subterminal object. Here's a recollement that you
Okay,
get for
okay.
free.
Nice.
And so the open piece is defined as follows. If I take an object, what am I calling my objects? E, I guess. If I take an object E, then I map that to the exponential object e to the u. All right. So this map is given by, so in other words, maybe I'll write it over here. So J star from e to the terminal object. So this is the map induced by the terminal map from u. And this is a localizer for the, this is the open localizer.
Right, because intuitively, if it was terminal, I'd be getting the global points of the elements of the thing, and
Maybe, yeah. Let's see. Okay, so this is so J star
almost gonna get some.
is a Lex reflector onto, I didn't actually give a name for my topos, let's call it curly E, onto E sub op. And E sub op, it turns out, is equivalent to the slice, E sliced over U.
Yep.
Okay, I guess this is a standard thing. This, I'm defining this. So E sub op is going to be the, so this is a reflector, so E sub op is going to consist of all the objects in E for which this is an isomorphism.
Wait, what's the map? What's the map from U to E to U?
Yeah, so where does this come from?
No, J star should take E to E upper U. That should be an object in the slice. Right?
Yeah, so why is this an object in the slice? Yeah, so there's a little bit of stuff you have to say. Like it's not this isomorphism here is not immediately obvious, and maybe I can just draw a little thing to give you some idea.
Opposites to all the E's for which the J star there is an isom.
Say again. E op for
That was the
open.
definition.
I am defining E open to be, well, I didn't define E open, so let me do a better job of writing this.
All the E's that are isomorphic to EU.
So I'm defining E op to be the subcategory that J star is a reflector onto, right?
It's essential image.
It's essential image, yes, exactly. Yes.
So EU.
So E op is the essential image of this, and then it turns out, fact, that E op is equivalent to the slice, and this follows from the following sort of standard adjunction. So maybe I'll put this in a little box over here because I don't want to sort of off the beaten path, but essentially if you have a, you have the pullback functor, maybe I'll call that U upper star. So this pulls back elements of E by the terminal map from U to give you things in the slice category. And then you have a
product.
Exactly.
Yeah.
That's what I mean. Yes.
Take the
Yes.
product.
Exactly. Take the product, right. Take the product. And then the other one is the left adjoint to this is the one that you get by just composing, right? So you have a map from E to U, and then just compose with the terminal map to get an object over here, or just forget, right? So this is like the forgetful map. But there's also a right adjoint, and the right adjoint is the one that sends, we'll call this U upper star. The right adjoint is the one that sends, so it turns out that E, the map that sends E to the U is the unit of this adjunction, is what it ends up being. But there's so it's a little bit annoying. So this was actually driving me nuts for a brief moment when I was preparing for this, because the exponential notation is ambiguous.
Yeah,
we were talking about that, because it's do you mean exponential as the right adjoint to, do you mean exponential as the right adjoint to the slice, or do you mean exponential as anyway, whatever. Too confusing. I would probably, it would drag on and on if I tried to actually do this. But, okay, so we have the open subtopos, which consists of the objects that are local with respect to these. And then we have the closed subtopos, and the reflector for the closed subtopos, the lex reflector, I sends an object E, so I'm defining what I of E is, and you take the join of E and the terminal map from U. So this is the projection to U, this is the projection to this, and you take the push out, and this is this object here is the, so this is the closed reflector. So take an object E and it sends it to cross with U, and then take the push out of these two projections, and you get that. So that's the join. Okay, anyway, so I just wanted to mention that because the next example is going to use this. So let me erase some stuff. Okay, so say goodbye to the fracture square. All right. All right, so I want to show a cool example from graphs. So graphs. So for me, I'm going to call, so let GR, everybody has their favorite GR. My GR, my GR is going to be the one that's a topos. So it's going to be, so my category of graphs is going to be the category of directed multigraphs, I guess you could say. So multiple edges allowed, self edges allowed. That's it. It's a topos, right? So it's a pre-sheet
maximum
topos.
possible, you call a graph.
Yeah, the nicest example of a category of graphs. The one that's a topos. So let's see. So GR is a topos. Let me just state some facts. So the product in this category is, of course, object-wise. But what that amounts to in terms of like actual graphs is a little bit counterintuitive. Like I find that a lot of this stuff is a little counterintuitive. But let me just give a couple of illustrative examples. So let's suppose I take this graph and I cross it with this graph. All right. So the product of two graphs, its vertex set is going to be the product of the two vertex sets. So this is going to be two objects cross two objects. So I'm going to have four objects like this. All right. Each one corresponding to a pair of objects, one of these two. And then between any of these two, you put an edge if there is an edge in between both the left and the right side of these two pairs. So, so for this product, so you can think of like this dot here refers to this pair here, right? I would put a self edge if there were self edges for both of these, but there aren't any, so there's no self edges here, right? This arrow here is going to correspond to, so I would put an arrow here if there was an arrow between these two objects, which there is, and an arrow from this object to itself, which there isn't. So there is no edge here.
I get it.
And there is no edge. In fact, it turns out the only non-trivial edge, the only edge you get is that,
Right.
I believe.
Yeah.
So that's the product of these two graphs, which is kind of weird, but whatever, that's what it is. What can I say? All right, and then let me just do another example. So if you had self edges, like if you had something like this, and like with the self edge, then the product would be,
With the diagonal.
yeah, so this one would be, you get all of these.
Okay, no, that to me makes intuitive sense if I think of like states in an automaton. I get from this state to that state. I can't stay in the same state. I have to change both states, which is why I only get the diagonal.
That's a good way of thinking about it. That's pretty cool.
But I think of dynamics, my graph is giving me arrows of dynamics,
that.
then
That's
I
pretty
can only make a transition.
Oh, okay. I like that. That's a good metaphor, yeah. I was just
Well,
like,
this is where Friday stuff in quantum field theory is coming in handy.
oh, really?
That's how I think of graphs as
Oh, nice.
dynamics, so.
Oh, cool. Yeah, I gotta let that one stew for a while. So that's so cool. So let me
At the
erase this.
bottom, you have a thing where I'm allowed to stay at the same state, so that's why I
Right.
have more options. Whereas at the top, I must change states, so the only thing I can do is change them both.
Yeah, no, I get it. That's a nice way of thinking about it.
Yeah, I like that. Yes.
So the terminal object, which is also the unit for the terminal object is, of course, just one thing with the self edge. This is the unit for the product as well as a monoidal product. What other things do I want to say? So the subobject classifier, we're not going to actually need it, but it's cool, so I want to show it to you. Because it's like, what? If you haven't seen this before, then it's like, I don't know, for me it's like, it's very strange. So here's the subobject. Has everybody seen this before? Oh, okay. So it's this.
Yep.
You have this, you have two vertices, and then you have
Oh, right, yeah.
loops like this. So this is a subobject classifier. So the idea is that if I want to classify a subgraph of a graph, then each vertex, so I have a subgraph, I send it to this if the vertex is outside of the subgraph. So if I have a subgraph, any vertex that's outside gets sent to that, right? And of course, if that vertex has a self edge, then it gets sent to this. If a vertex is inside the subgraph, it gets sent to this. And then if any edge that is included in my subgraph will get sent to one of these, and then any other edge will get sent to the other one. So if I have two vertices that are in my subgraph connected by an edge that is not included, then I send it to this. I send that edge to this.
Bill Levere called that,
what in the-
Bill Levere called
That's
that
crazy.
foray.
Foray?
Yeah,
What's that?
it's a
mean?
foray. Outside the sub.
F-O-R-A-Y.
Oh,
He called outside a foray.
oh, cool. Okay. Yeah, I don't know. This is all very new to me, so I'm like,
Can I ask you
you
one
know.
favor?
Yeah.
Ask me about color chalk. Could you color the inside loop and inside dot in color? Because that's going to be the true thing.
The inside, this to the, and this
Yeah,
will be
that.
the true. Yeah, sure, why not? I don't know if I actually have, the only color I have is yellow, but I'll use it.
Yeah, that's fine.
So this is the, this is true.
Anyway, Bill Levere wrote a paper about this
Oh, cool.
topos.
Nice. What's the, do you remember the name of it? I want to read it. Do you remember the name of the paper?
Taking categories seriously.
Taking categories.
Well, who knows if it was ever published, but,
Hegelian Techo.
no, it was as exemplified by directed graphs or something like that, as part of the title.
As exemplified?
Okay, let me look it up here.
Yeah, so,
Foray, F-O-R-A-Y.
4A, okay. I think that's probably enough for me to be able to find it. That sounds like a fun paper. So let me just say what the representables are. So I'm going to call, so in the category here, of course, we have edges and vertices, so I'll call these like E and V. Okay. The representables are going to be,
I'm working, I just only just opened it up yet.
so I'll just call the representable Yoneda, Y for Yoneda of V, ends up just being this graph.
Well, not, the word foray is not in there.
And then Yoneda of the edge object
See what we get.
is this thing. Okay. Okay.
As exemplified by.
Was V and E again?
Maybe I'll just draw it like this.
Oh, okay, thank you.
That's
Two objects in that category there.
Yeah.
Yeah, so these are the two representables in this category of
Every graph can be built up
Diagrams.
from those.
Yes, yes. So I mention this because this category, of course, has an exponential, and the exponential is weird. The exponential is sort of strange, at least if you're me. Maybe if you're Ray, you know all about it. But I found it a little bit strange. So the exponential, I'll just say what it is.
Let's see if I can figure it out.
I guess.
Why? I won't figure it out, but maybe I can understand after you do
They
it.
might have it as a reference.
Oh, yeah, that
though.
makes sense.
Yeah, right.
So if I have a graph F and a graph G, then G to the F, the graph of maps from F to something like that. Of course, you know what it is. It's the standard thing. But what it works out to is the vertices.
This one might be the one you're looking for. Qualitative distinction between subtotals.
The vertices are, of course, by definition, Hom from F cross the vertex, the V representable, Homs for F cross Y of V to G. And the edges are, of course, Homs from F cross.
So how did you find?
Y to G.
I just changed it to horizontal, so maybe I'll change it to horizontal.
You just went on Google.
It's not that strange if you know simplicial sets.
They give me.
Yeah, you know, it's, I just like, I don't know how to, I don't have like a nice picture of it. Like I want to draw a picture, but I'm like, I can't really draw a picture. Like I can think of like, so if I take, so here's a fact, like if I take a graph F, taking the product with just the dot here, the effect of that is you get the same set of vertices, but you get no edges
Yeah.
because this doesn't have a self edge. So taking the product with the dot just throws away all the edges,
Yeah.
is the effect of it. And so now I have the set
Map all the
of,
dots to the dot to every, something in G.
yeah, exactly. So this is gonna be, I'm gonna get one vertex in the exponential for every set map from the underlying vertex set of F into the vertices of G. And I get all of those are gonna be the vertices of the exponential. And then here, F cross this thing to G, that gives me the edge sets, and like, I don't know, I mean, like, I don't have like a nice pithy way of saying what that is.
All the actual graph homomorphisms are the self loops. Yeah, on the vertices.
Oh, really?
So easy to-
Huh, all right, I gotta think about that later, okay. Anyway, so this is just a rundown. Okay, finally, there are three subterminal objects. There's the empty, there's just a dot, and then there's the terminal object. Okay. Obviously, these two are going to be a little boring, so let's focus on this subterminal object, and let's do the thing I was just describing, wherever it was. All right. So let's do this. Let's choose the thing I was calling U before to be dot. Okay. So what is the open subtopos? Let's erase all this. Do I need anything? Well, anyway. Okay. The open subtopos consists of graphs I'll call them G, for which G to the terminal object, which is just G, is equivalent to G to the dot. So all objects where that localizer, where I take the exponential, is an equivalence, those will be the objects in the subtopos. So, all right, so what is G to the dot gonna be? So, G to the dot is going to be.
Graphs.
So let's think about it. So going over to the description of the exponential object, right? So if I let F be dot, then the vertices are going to be just the vertices of G. And the edges are going to be maps from dot cross this, which is just two vertices. So two pairs, the set of
The complete graph.
exactly, it ends up being the complete graph. So the subtopos is the complete graph. So G for which consists of graphs G for which G is equivalent to that, i.e. complete graphs. So complete graphs are the open boys, all right? And then the closed subtopos. By the way, I stole this example from a Stack Exchange post. It wasn't on Math Stack Exchange. It was on the Proof Assistance Stack Exchange. Somebody wrote this up so beautifully. His username is Trevor, but there's no other information I can find for
It's
it.
like clicks and the composition of your graph.
I don't know. I mean, let me finish the example and then we can, all right, so complete graph. So the closed subtopos, so what is it? So the closed subtopos consists of G such that, so what is it again? So the localizer for the closed subtopos, so the I upper star functor, took G, right? So
Like the blackboard next door.
Oh, how do you like that? Except now it's a G instead of an E. Yeah, so exactly. So it took G and then it sent it to the push out here. So an object is local with respect to that map if I just put G here, right? And then of course this is the identity. This is a push out. And then it follows that this is the identity too. Oh, U is a dot, sorry, right, I forgot. Yeah.
So that means it has to be discrete, right? Because G times dot is G without any edges.
So let me write it. So this consists of G such that this is an equivalence. So such that, well, I'll just go to the next board. I'm all over the place with the boards. Such that G cross dot is equivalent to just dot. So what is G cross dot? It is take a graph and throw away all the edges. Now you have the vertex set. The vertex set has to just be a one element set. So it'll be graphs with only one vertex. So
loops.
Graphs with one vertex. So these are the closed thingies. Okay? And then we get a recollement, which is, I'm going to draw it over here. So let me just draw an example, okay? So suppose we start with a graph, this one. All right, so this graph here, all right. The open map is going to send this graph to the complete graph. Where on this,
the arrows that aren't there.
So just send this to the complete graph. So we have this dot, this dot, and this dot, and also these. So lots of arrows, every possible arrow. All right. So this is the open reflector here. I guess I'll say, well, anyway, it's a subcategory, so I don't have to write that. All right, and then the closed sends this to the graph I get when I just pinch all the vertices down to one vertex. So I get just a vertex and two edges like that.
So let's see, so the basis of one, so J star gave me the vertices because it messed up the edges, and the I star messed up the vertices but left me the edges.
Exactly. So when you take the J star, you keep the vertex information, but the edge information has been effectively thrown away. And then the other way around here. So here all the vertex information gets thrown away, but you keep the edge information,
That's a
right?
very interesting concept.
Yeah, and then here in the corner, if you remember many boards ago, there was, it was like the I lower upper, J lower upper, so that was like take the open reflection and then the closed reflection of that. So what's that going to be?
You take the complete on that, but that's already complete.
So if I take this, so this was J, so the thing I get here is I get by applying the I star to this thing. So this is
This.
So then you have three loops.
right. So this was the I star, right? So
we should have one,
this is
2,
going to
4,
be
5, 6.
Oh no, you get a bunch of loops.
this is going to be crush all the vertices together, and then I have one vertex with an edge for every possible a loop for every possible edge. So how many of these? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have to draw 9 loops now. Here goes. 1, 2, 3, 4, 5, 6,
Get a flower.
7, 8, 9. There it is. There it is. All right. And then of course I have this and I have that, and then this is so this is the fracture square applied to this graph here, right?
Yeah.
And that gives you.
Well, I'm not exactly clear how you get from when you do I star and then you would apply J star to it, right?
This
How do you
was-
end up getting 9.
I forget, what was it? It was
What would be the way
to
to-
apply the I functor to the J functor, to this map, right? So it was like the map induced on the crushings, right? So basically, yeah, it's like So this map here sends like these three vertices to these three vertices, these two to certain two here, right? And then these two edges get sent to a couple of loops here, right? And then this map here takes these two edges, sends them to these two, and those two get sent to the exact pair of edges there.
Yeah.
Well, the important thing is in the flower,
Okay.
the vertices got encoded by
Yeah,
the loop
okay,
on
I think I'm
on
getting
each
it now.
vertex.
That's what.
Yeah.
This is really awesome.
Isn't this cool? This is like the funnest example.
Recover the, once you
So-
recover vertices, then I can recover the ones edges between them. Okay.
Yeah, so that's an example of a recollement in the context of a one topos. So the first example I gave with the open and closed was effectively a zero topos, I guess you would call it a locale, right? So next I want to talk about the next level up, and I'm sorry, am I?
No, you're a little
Can-
bit, I'm going to be running out of video, so you
All right.
go on. I'm just going to stop at some point.
All right, let me just see how far I get. So the idea is that the sort of my motivation for giving this talk was that recollement show up in differential cohomology. They're sort of like the main thing that differential cohomology comes from. So let me see if I can get there, at least the beginning of it. Stable recollement. Okay, so now we're going to be talking about categories that are infinity categories. So let C be an infinity category. So C an infinity category for starters. Maybe I will say, well, let me draw the thing I have to draw first. So I'm going to have K. Yeah.
You give the definition.
Just think of a category. It doesn't.
Nonsense or what?
Yeah, the spaces up to weak equivalent.
Yeah.
Just think of categories. Anything, so regular categories are infinity categories, so you can just think of categories. So we have the three things like this from before, last attempt to space them out well. So we had I lower star, and we had, right, the left adjoint, I upper star, and we had the J restriction and the J push forward, like this. So under certain conditions, you get an extra pair of adjoints. So those conditions are, I'm going to rattle off a few examples of sufficient conditions, but I don't actually know like the exact set of conditions under which you get these. Like I don't have a pithy way of saying it, but I will say that if C is a stable infinity category, so let's let C be a stable infinity category.
Just the infinity version of an abelian category.
So if C is a stable infinity category, then you get I upper shriek, which is terrible. This notation is like really not very, Blackboard friendly, but.
Think of spectra are like infinite.
Do products equal co-products?
Yes.
And J lower shriek. Yeah, so a stable infinity category, I'll just remind you, the definition is really quick. So it's an infinity category with a zero object, finite limits and co-limits, and pullbacks or pushouts. Simple as that. I'm pretty sure that's right. So let's see, be a stable infinity category. Right.
Like our infinity.
So there's a zero object in a stable infinity category, so it's not going to be a topos. Or an infinity topos. It won't be. But if C is a stable infinity category, in this situation, you do get all three of these things. All right, so let me just say, now I'm going to state some sufficient conditions in general. So if K has an initial object, so I'm sorry that I'm writing this. So for these assumptions, I'm saying, suppose that.
In words.
All right, let me shut up. All right, well, there's a few things I have to write anyway, so I'll just say, if K has an initial object comma, you get the J lower shriek. So any category that, if you have an infinity category that not necessarily stable, but does have an initial object, you get that. Of course, a stable category does have an initial object by definition, so you always get that. Okay, 2, if C has a 0 object, as stable infinity categories do, you get an I upper shriek. You get this map, the right adjoint to the fully faithful functor here, fitting into, so such that I lower shriek, I upper shriek, I lower star, upper shriek, 2. The identity on C, 2. J lower star, J upper star is a fiber sequence.
Topological group.
And space is an infinity category.
So you get a, so we have a 0 object, so we can talk about fiber sequences because we're effectively in a pointed category now. You can talk about fibers, I mean, unambiguously. And then this is a fiber sequence. So essentially the way you end up defining this thing, you just define it to be the fiber of this thing. Like if I take an object in C, and then I take the open localization of it, the fiber of that map, I just define I upper shriek to be that fiber. So you get this fiber sequence, okay? And also, can I erase? If C is stable, so this is 3. So this was up to here, we just needed pointed. If C is stable, you get J lower shriek. No, wait, we already had J lower shriek. Yeah, right, you get a you get a fiber sequence. J lower shriek, J upper star, to the identity on C, to I lower star, I upper star, a fiber sequence. All right, so in the stable case, you get all of these things. Let me just say that, just a fact that I'll state out loud. So in the situation of a stable recollement is completely determined by the closed subcategory. So if you have a stable infinity category together with a closed subcategory that is both reflective and co-reflective, then you get this for free automatically. So you get the whole recollement for free. That's just an interesting fact. I don't know.
Okay,
yeah.
but I guess that's kind of like in the groups. So I was saying if you had, product, if you have a billion groups, once I give you the normal, all the subgroups are normals.
Yeah, exactly.
So
I mean, the whole...
gives you the other thing.
Right. I mean, the whole idea is that a stable infinity category is like the infinity version of a abelian category in some weird way, right?
Sheaves of spectra, what is K in that?
So yeah, let me draw the diagram and then I can tell you the conclusion. So maybe I'm going to skip the derivation of all this and just write I'll just write the last diagram here. So maybe I'll write it here because this is and then I can point and talk for a little while. So skipping where this comes from, you get the following diagram. So here's the identity on C. C is a stable infinity category. I have the open and closed reflections here. I lower, I upper. And I have I lower, I upper, J lower, J upper here. Okay.
So you just
And this is the, so if I have a recollement in a stable infinity category, then this is the fracture square, the standard one from before. This is in a stable infinity category, since pullbacks are pushouts, instead of putting the little hooky thing, they put a little square. So this is a pullback / pushout in a stable infinity category. Yeah, I hadn't seen that before either. So then we get, so this is a fracture square, but you can extend it out. So remember, we have these fiber sequences, right? So the fiber sequence here, I can just put the fiber I star, I lower star, I upper shriek, I lower star, I upper shriek. This is the fiber of that. And then this composition gives me this. Similarly, I can put the fiber here, J lower shriek, J upper star, and that's the fiber there, and then I get this composition here. And then by the stuff that I skipped over, you get another pullback square. Well, you can just define it to be the pullback square. Yeah, you just define it. But I guess the argument shows that the thing I put here, this pullback, is actually loop of I lower star, J lower star, J upper star, like this. And that's another pullback square.
Why do you use omega? What is that?
This is the take the loop space functor, which is the same thing as the inverse of the suspension functor if you're in a stable infinity category. Okay. So loop is suspension inverse.
I have some homework to do.
Yeah, so basically, I can say more about it. Like, so essentially if you have in general, you can define the loop space as the homotopy pullback by two maps from a point. So if you have, anytime you have point space here, the pullback is the loop of that. That's like the definition. Okay, so this hexagon diagram is sort of, I guess maybe the abstract general incarnation of this famous diagram that you see in differential cohomology theories. So in differential cohomology theories, you get, okay, so I guess now I'm going to talk a little bit about, so this is maybe I'll just label this. This is the differential cohomology hexagon. Hexagon.
Very well studied in the grad center.
Yes. Yes, indeed. So let's see. So what was your question again? What I was delaying?
What is K for sheaves of spectra?
Okay, right. So, so the way you get a differential cohomology theory from this is that you take your category C to be the category of sheaves of spectra on the site of smooth manifolds. So which, the site that you know so well, like you can use Cartesian spaces or just all of man, whatever. But sheaves of spectra, so that's stable here. Sheaves of spectra on manifolds. There is a functor, so the open subcategory here, sorry, this is the closed subcategory. The closed subcategory ends up being spectra. So in general, like if you had, if you weren't in the stable case, like if you had like simplicial presheaves on the site of manifolds, then you could take the smooth sing, right, the sort of, the thing that takes a simplicial presheaf and spits out a shape, right, shape, then spits out a sing. Is that the same thing as smooth sing, right? That gives you a simplicial set from a simplicial presheaf on manifold. So that's like that incarnation of the shape thing. But in general, it takes this whole, you take this whole simplicial presheaf and it gives you like a homotopy type. And then the version for spectrum is like you have a sheaf of spectra and then it will give you just a spectrum, just the topological side.
Matt, let's just finish the video. So say something nice to the video.
Okay.
The batteries.
Thanks. I'm basically done.
We can sit here for an hour and talk.
I pretty much finished the talk and now I'm just rambling about.
Thank you very much.
Thank you.